This is going to be the example 3 try. This problem is also located on page 251 and it's number 13. An airplane is flying at an altitude of 7 miles in the air and passes directly over a radio antenna. When the airplane is 10 miles from the antenna, the distance between the antenna and the plane is changing at a rate of 300 miles an hour. What is the speed of the plane at that moment? So the book draws it for you, but let's draw the model together. So right here is our radio antenna at the bottom. That's our little radio antenna. And we have our plane, which is over here. So we know that the distance between the radio antenna and the plane is 10 miles. We also know that the distance from the ground is 7 miles. What we don't know is how far away the plane is this way, so we're just going to call that x. That means any time that the straight distance, or s, changes, it's ds dt. Any time that it changes, it's ds dt, because it's the change in the distance divided by time, or divided by the rate. This distance right here, this is going to be dx dt, because it's the change in the distance horizontally over time, which is also known as speed. And then the 7 miles never changes, but we're going to call this y. So it's very important to write down what we do know. Well, we know that y is equal to 7. We know that s is equal to 10. We know that ds over dt is equal to, well, let's look at the problem. We use that it's 10 miles from the antenna. We use that its altitude is 7 miles. S is changing at a rate of 300 miles per hour. So we know the change in S is 300 miles per hour. Now we're going to write down what we want to know. What we want to know. We want to know dx dt, which represents the change in x, which is also the speed of the aircraft. So what we need is we need to set up a formula that relates the two. Well, if you look, this makes a right triangle. So we have x squared plus y squared equals z squared. And so what we need to do now is take the derivative. So we're going to take the derivative in respect to time. So we get 2x dx dt plus 2y dy dt equals 2z dz dt. I'm going to divide those all by 2, so the 2's cancel off. And I get x dx dt plus y dy dt equals z dz dt. Now let's plug in what we know. Well, do we know x? No, we don't. But we can find out how far it is. So we're going to use our triangle. We know this is 7, and we know this is 10. So we get x squared plus y squared equals z squared. So x squared plus 7 squared equals 100 squared. X squared equals 100. X squared equals 51, and x is the square root of 51. So from there we're going to go the square root of 51 dx dt plus y, which is 7. Now the change in y over the change in time. The question is, does the height ever change? And the answer is no, the height does not change, so this is going to be 0 equals z, which is 10, and the rate that that's changing is 300 miles per hour. So we get the square root of 51 dx dt is equal to 300,000. And then we go ahead and divide by the square root of 51. And we get that dx dt is approximately 420.084. This means, so now for our summary, this means that when the plane is 10 miles away from the antenna, it is traveling at 420 miles an hour. So when the plane is 10 miles away from the antenna, it's traveling at roughly 420 miles an hour. And that's it. Yeah, I don't think these problems are too difficult. They're just, the initial setup is a little tricky.